Yeah, I'm all set. So, good morning, all of you. Okay, for so people in India, it's afternoon. Um, so just to give a brief background, like why we are taking this and what we will cover today. So, I assume that all of you at least have some exposure to analog IC design course, and today I would like to uh, take this session more towards the simulation, how quickly one can design a working circuit and then later optimize. So the time, I would say that how closely you reach to 80 to 90% of your design of your block. So we'll see some of the current sources, biasing and band gap. So these are one of the building blocks, very important building blocks in any system. So it's So we'll start with this assumption, and the first thing um, I would like to start with is the current source. So why? Because this is widely used in many of the blocks. So how we will design this? So before that, we need to see what is an ideal current source and how, when we go to transistor level, what care we need to take. So when we start, if there is any issue with the audio or if anything is not clear, so you all can interrupt. So if this is an ideal current source and I want it to design for 1 microamp current, and if there is a potential across it, sometimes we call it V compliance or anything. If it is transistor level, this is called VDS. So suppose we have this value 0.9 volts and we take three examples and this is 1 micro and you apply 150 millivolt and this you have again ideal 1 micro and this is 50 millivolt. Do you think in all the three cases you will get exactly 1 microamp if it's an ideal current source? Anyone?
If we are meeting the compliance, then we should.
Yeah, if it is an ideal, it doesn't matter, right?
Yes.
So even for 50, if you take it minus 1 volt, even this, then also this current source will be able to provide 1 microamp current. But when we go to design a current source with transistors, this doesn't work. So you need some compliance. So how we should decide that what, so let me replace this with a, we will see how we will select the WL, but let's start with, so this is 0.9 volt. And again, you have 150 millivolt. And in this case, 50 millivolt. So let's assume that this, so this is in saturation. Why we need into saturation? We will see it later. So do you think if you design a current source, this is a unit block, all three are similar, exactly the same. So if this current source works, which has 150 millivolt VDS, will this work as well? It is moving. Any
Uh,
comment?
y- uh, yes, sir, it should work. If
Yeah.
VDS is greater, then it should work. Greater than 150
Yeah.
millivolt.
Yeah. If suppose this 150 current source is working, so if you change this drain a bit higher, will also work.
Yes.
So what does that mean is we should design our current source for minimum VDS. Let's assume if we design a current source, And if while designing you take care of this, that any current source which works at minimum VDS, let's say it's 150 millivolt you design, and we will see how we will bias and how we select the W by L. But the idea is this 150, if it works, if it is 200, if it is 400, 900 millivolt, it will work. So why this is important is mostly in output stages. Suppose you have a current source load in one of the output stage. Suppose this NMOS is your current source. So this node is swing dependent, right? And so if this is your VDD, this is your ground, so this potential can reach to a lower point. So we need to make sure that even if it is at this lowest point, the current source remain in saturation. So this way, whenever you have an output stage, if you see any data sheet, it always talk about, okay, there should be some margin we should keep. Your output cannot reach rail to rail. For rail to rail, you need to design in a different way. But this is one of the assumption, like we need to keep VDS as low as possible so that even with high swing, this remains in saturation. Is this clear till this point? Or you can add any of your um, you can
Yes,
Yes,
comment.
clear.
Okay. So the next thing, yes,
Sorry, Mirad, I have a
yeah,
question. Do
yes.
you mean keep VDS low as possible or V overdrive?
Okay, okay. So yeah, so V overdrive is the second part. But when first we need to think that our current source compliance, which I call it this this compliance, that our current source should work for a minimum VDS. Any potential across that, across the current source, it should establish at least that much. Then only the current source should work. So based on your VDS, you decide your overdrive, which is your VGS. So,
Okay.
so, so in any op-amp design or any circuit, so you should make sure that what is the minimum VDS you can tolerate. So if you have 1.8 volt supply, your VDD is high, so you can easily keep 150, 200. But if it is low supply, then you need to think, because if this VDD is suppose 0.8 volt, there are some 22 nanometer technology you have. So now total voltage drop is zero point 0.8, and if you need a swing of zero point 0.6, then you will only have 100 millivolt here and 100 millivolt. So your current should work at 100 millivolt. And if you are constrained, sometimes you need to go below 100. So this is something which is not a spec as such, but from swing you can think of come to this point. Okay, so now this was just from point of view of VDS. So if you see any transistor, what what are the variables? What are the knobs which decides the current? So this square law, uh, you, we all have seen a lot from our undergraduate till now. So you have VDS, VGS, length, and W. These are the parameter which affects your current. So this decides by this swing, and I would say also the supply decides like how much VDS you want to keep for the current source. Now the second question is how you set your VGS. So there are like the transistor can be operated in various regions. So one is saturation, subthreshold, linear, cutoff. So how this VGS can be selected? So I can show you one table. So this what you see here on the left, this is cadence specific. In cadence, you can see the region in which a transistor is operated, and this is like your VD should be greater than VB minus VT, which is the overdrive. And mostly you operate your transistors when you want to work as a switch in this operating region, and amplifiers current source can be used for saturation and sub-threshold. Let's take, we have already know that we need the current source to be biased in saturation region. So what is the condition of VGS? How we can select the VGS? So if we don't want sub-threshold, sorry, this is the uh, this is the condition where if you violate this, you will get into linear region, and after this is your sub-threshold. So what flexibility you have for VGS selection? So to be in saturation, one is it should be greater than VTH, and the second is the VDS min we discussed before. The VGS should be less than VDS min plus VTH. So this, it is just rearranged a bit. So as a designer, selection of VGS, you have only this value. So suppose it's around 500 millivolts, and you target your VDS for 100 millivolt, and this is your 500. So as a designer, you know now that, okay, you can only be between 500 millivolts to 650 millivolts. So this is the choice of VGS you have. So now a question comes like whether we should be on the lower limit or a higher limit, because all these value will give you. So just for so this is like I took one example, like I took an ideal source, current source, 1 micro, and just applied the same thing which we discussed, and I just kept 550 millivolt because I'm using TSMC 180 nanometer technology. This is just to show that you can, when you run the DC simulation and then you annotate, you can see the regions, GM, VTH. So suppose you are working on a new technology and you don't know, so the best thing is start with any simple, because in analog, I just started with 500 nano cross, 500 nano W by L. In analog, you don't need to be very precise because you have process variations, you have temperature variation. So, and W by L, all this matters. So just start with one simple, take a transistor, just make sure you are above VTH. That's it. And this is how you get your current and regions. So what happens when you are 50 millivolt if you put across? What degrades from saturation to linear? So the degradation is your R out reduces. This is one of, for an ideal current source, R out is infinite, but in most cases, to have a very high gain, we need a very high value of R out. So yeah, so this is how like uh, below, if I am above this VTH, I'm sure I'm not in sub threshold, but I need to make sure I don't cross that limit of VDS. So if you select a very small VDS, then you need a, your VGS minus your overdrive requirement will be very high. Okay. So how, so this was just like how in Cadence you can start a, with just your VGS. Anything low greater than VTH will work, and it work in saturation and you can get a current. But the next question is 550 enough or 600 is better? Can anyone comment like uh, if you want to design a current source, which VGS value you should keep? In this, let's take this is, okay, let me write it here. So if you have a two case, let's have a two case. Is 550 millivolt or 600 millivolt? Which one we should select if you want to design a current source? I know it's very application specific, but as a designer, what do you think? Which one would be better? If you want, you can guess also, it's fine. Then I can ask why you think 550 is better or 600 is better. Anyone would
Uh,
like
I,
to? Yeah.
I, I think if I know the VDS minimum, I would like to have the 550 millivolts to have higher VDS and have a higher R node.
So if you have 550, what benefit you get? Can you
Get
please repeat?
higher VDS and deeper in saturation, you get better R node.
Okay. So you are suggesting smaller is better. But VDS, you
Maybe
see,
600.
yeah, 600 is there. So that is what we are discussing it so that we can arrive to a solution. Because if VDS is fixed, that if you know your swing requirement, the lowest your voltage will go across any current source will be 100 millivolt or 150. Then how we select is one criteria is mismatch. And then we will see there is also noise. So I will quickly go through this. If you see this is a standard current source equation, and what I'm doing is I'm just replacing UNCR W by L with beta, just so that the number of variables in the equation can be reduced. So calculating a difference equation, what difference equation is, this ID depends on three variables. And if you write a difference equation, you keep one, you differentiate delta B and keep the rest as it. Then you differentiate for VTH, delta VTH, keep it. So by doing this in a current source, this is pure mathematical. You arrive to this equation. And if you have a current source, so when I say, if I have this current mirror, so you see these two VGS is same because the gate is same and the sources are same. So when you have a current mirror, your delta VGS will be 0. And then you just simplify it. And when you keep this delta I by I, you arrive to this point. And if we write in statistical form, it's just similar to this, like any variable, if there is statistical variation, you just square it and add. So now just seeing at uh, these terms. So what are the variables for mismatch? One is your there are three variables. One is this delta B by B. One is delta VTH mismatch, and there is a VGS term here. Um, so now if you see this VGS is in the denominator, and your mismatch. So now higher VGS is better or lower VGS is better if you see this equation. So higher is better, right? If you increase the denominator, this whole term will go down and your mismatch will be less. So suppose you are designing a current steering DAC in which the building block is your current source. So you have a lot of current source connected like those. And if I say it's a thermometer, this is I. So in that DAC, I want this mismatch should be as low as possible. So what VGS we will select, how we will select this to the extreme, whatever VDS allows. Whatever VDS min allow, you try to keep the VGS at the highest as possible. That is deep saturation. So from those mature technologies like 180, this term is dominant. The VTH variation is dominant, a variation compared to, so you can say that A VTH is greater than A beta. So these are just something which a Foundry has there in their models when you do some Monte Carlo simulation. So right, so the key takeaway is always try to bias the VGS as high as possible so that your mismatch will reduce. And this is one of the takeaway. Now, just as we said that VTH is higher, can we simplify it further? So we know that this 2 by VGS minus VTH can be written as GM over ID, and this variation can be simplified. This is based on this assumption. Don't take this words like universal, because maybe in future technology nodes this may not be that valid. But yeah, at least for 65 and above, you can say that the threshold variation dominates the variation. So this A beta is because of any variation in mu and post fabrication and W by L due to size. Okay, so now let's do a bit of simplification. This GM over ID can be written as 2ID means a W by L and replacing this. So you get one more constraint, like how you decide. So one was keep the VGS maximum. Just by seeing this equation, you get another one. Also, increasing L helps in reducing mismatch. This is something you might all have seen, or that the greater L is better, but we can derive it from this way. So if you have a fixed current, suppose 1 microamp current you are interested in, and if you want a better mismatch, you will always choose as high L as possible. So L increase is like you have a penalty in terms of area, but this helps. And also, is there any other parameter which L helps? The R out. R out is 1 by lambda ID, and lambda is proportional to L. So this is also one more reason like why we use longer L when we need a, suppose in gain stage, we need higher R out. We select a better L. So mismatch and this. So now we will, one more parameter is, okay, so one more parameter is the noise of the current source. So if we take any transistor, so there will be some current noise. I if I'm going a bit fast, you can slow me down. It's something clear. If you design a current source with I, so what is the noise component? 4 kT gamma gain, textbook stuff. So let's play with it, just rearranging some a bit of mathematics. You can divide ID by ID. It won't affect your expression. And GM over ID is 2 by VGS minus VTS. So again, you get a VGS here. So if you want a lower noise of your current source, you should have a higher VGS. Right? Because if current is constant, the only way to reduce noise is increasing VGS. So, okay, now again come back to this and let's revisit. So if we want to select a VDS, so this we can select by swing requirement, and how VGS is selected from mismatch and noise, right? And when it comes to L, how we select L? This is from R of point of view, and then second, which we all see from mismatch. And then W is just a scaling factor in the end we do. I will show one the way it works for me, and it can work for all of you. Just quickly, you can arrive to a current source design. Let's go to our CUDA. So is this clear, right? How you select each parameters, how it is available. So this is like a design space. It's like you will get a penalty in one thing or other, but this is a quickly how you can arrive to a solution. So what I do is, I will take an NMOS from a library. I will just give a variable length, width, and this is my VDS and this is my VGS. And similarly, this is for PMOS. If I take a PMOS, I will put here VDD, because in real scenario, the source at higher potential is VDD. So what if I want a VGS similar to what I have here? What I need here is VDD minus VGS. So effectively, you get VGS here. This is VDD, this is VGS. So similarly, if this is VDD, if I want VDS across this, I will put a variable VDD minus VDS. Okay, so I will go here and 150 I have kept, supply is there. And I know from like very basic simulation that my VTH is around 500. So I have kept this 550. And length based on mismatch, output impedance, we go. And now suppose I will, let me make it 1 micro and 1 micro. I don't know what value of W I should keep. So I will run this. So I will get a, a value of current in both NMOS and PMOS. So my current here is 885 and this is 283 nano. So without changing uh, my GM or other parameters, how I can reach to 1 micro target if my target is 1 micro. I may delete this. Three. Okay, fine. So what I can do is I will go here. I can sweep width from 1 micro to 10 micro. It's just automated one. And I have these two current sources. So this is for my M3 is for PMOS. And we have this for M1. So by this, what we can see is, so I have swept the width. This I can make it. So where I am hitting 1 micro. So it's around 1 point, how much? 1.1, right? Or 1.2. If I keep my width as 1.2, I can easily meet the 1 microvolt current. So I can make it 1.2 micro. So now again, I will go back and just change it to CMOS. And it's just a sweep. So I'm just measuring the current. I'm changing only one variable. So I see that my 1 micro would be around 3.8. So 3.8 micro. So, so tomorrow, if you use suppose you use another flavor of the MOSFET, so you can start in a similar way. If you can see both are across one, so it's a bit less I can make it. Till now, is everything clear? So yeah, so this is my what I call it a unit block, unit transistor, unit device or base device. Now I have this reference. With this, I can I can implement all other blocks with this unit block. So I know my GM, if I keep it this value VDS 150, VDS it works well. And if you see VDS that is 115. So your device will be in saturation till your VDS is 150. So I kept 150 for a margin so that across process also it can work. So that when you run process corners, you don't see that, oh, it's failing in some of the corners. Okay, is this clear? So then we will move back again. So this is how I can design a current source. So now the thing is how you use it in a real chip. For that, we need a beta multiplier. Okay. Can anyone tell why we use a beta multiplier? But till now, we were talking about, okay, we want to make a current source, we want to make a current source. Then, so in that current source design, I can write here. In this current source, we we took ideal VGS and we started with this. Okay, we kept this. Okay, I need this 550 millivolts, and then I thought my current source is ready. But in the end, on chip, where you will generate this 550. So there are two ways. One is like just use a current meter and bring a current from outside. So you just bring 1 micro. So you're the same W by L, the unit element which we sized. We can use the same W by L and we'll get approx VGS which will help us to bias this. But you need a current source externally. So what we do is we don't use this current source. So we can do it by on chip generating the bias. So for all NMOS, this is V bias N, this is V bias P. So anywhere in the chip, if you require a PMOS source, that's it. Take this will be gate. And anywhere in NMOS, if you want a current source, just take this. Multiple places. And in all our design, we have assumed one thing that we have designed this for 1 micro. So if so, this is the W. So in the design, wherever you need 2 micro, just make it 2W. Wherever you need 5 micro, make it 5W. Don't change anything. No need to change the L. Everything will set automatically. So this is 2 micro and this is 5 micro. And this is a resistor R. So I will not go deep into how a beta multiplier works. So in any book or course it is there, but from design point of view, what are the important part? What are the equations which can guide us? If you see, this is your VGS1 and this is your VGS2. So the unit element, we have selected WPLP, and you have WPLP same here. Right? Similarly, you have the same WN which we used, which we designed for current source. We use the same WN by L. Here, the only difference is since we have a resistor here, we need to scale this width because if you want same current flowing through here and here, IREF is same is only possible then if your VGS different because there will be some drop across R. So just put a KVL loop here. So what is the key equation I'm just trying to derive? VGS2 is equal to IREF into R. Because for designing a beta multiplier, we already know the sizes of WL of all transistor. This R is how we select this R. So this is something I'm trying to derive. So what value of VGS we can put? So this is if you from the current equation I is equal to mu and C of W by L VGS minus VT whole square, you can extract VDS. So this is 2. So what will be this value here? 2 I ref by mu and P of W by L. And here will be minus VTH minus root under 2 I ref by mu n C of W by L with a K here is equal to I ref into R. So just VTH gets cancelled, and what you get here is root under 2 I ref by mu n C of W by L. Just quickly simplifying it into I ref into R. Okay. So I will keep 1 by R, just rearranging the terms. And this will go that side. This will be. So can we write this like this? 2 I ref mu C of W by L, and this 1 by 2. Just arranging this. If you see this term, this is the GM. Mu n 2 ID mu n C of W by L. And if you put K is equal to 4, what will happen? So this will simplify to, if you make K is equal to 4, then GM will be how much? 1 by R. So have you seen this when beta multiplier somewhere? Anyone? Okay. So okay, so this term, this GM is equal to 1 by R. This makes the, so okay, for that, what was assumed? I think this, let me share it again. There is some issue here. Okay, so if you see these three names, beta multiplier, constant VM biasing, supply independent biasing. So these all three names you will find in one or another book. Like Razavi also in Razavi's book he has mentioned supply independent biasing. Baker's book you will have all these terms he has mentioned. So why we say constant GM biasing? Because now the GM is dependent on this R. So whatever bias this generates, then if you use a current source, the GM will be dependent only on R. And there is, if you see the current value, it doesn't have any relation of VDD. That's why it is called supply independent. So this is the relation in which you have current. We simplified from GM point of view, but if you take only the current and simplify it, there is no VDD term. That's why it is called supply independent biasing. So for 180 nanometer, this, because VDS is sensitive, we try to use it. But let us see like how we can, in simulation, how we can quickly design this beta multiplier. Okay, so we know that GM is 13 micro. So what value of R I should keep? If I want to keep GM is equal to 1 by R, then 1 divided by 13 micro. So how much, can anyone say how much will be the resistance value? So it's
77
around,
kilo.
yes, 77. So what I will do, what I have done is I have taken this transistor. Okay, I can show you. I have just arranged it here. So this is length PMOS, length NMOS, exactly what I got from here. And I will just plug this here. This is PMOS. Only change I did is here, is I kept multiplier 4. So that my equation simplifies to 1 by R. So what I did, from my unit element design, I just took the GM value of 13 and I plugged it here, resistance. And if I see here that it's approx 1 micro. The reason it's less is because we assumed it is square law, but quickly you can design a beta multiplier with 1 micro. Now the issue is it's not completely supply independent if you run the simulation and see all this. So what we can do is, because the reason is the VDS is different from both sides. So to make it similar, we used a OTA which just drives the we just sets this value. So in this case, how we go ahead is we take two transistors. So this is our 5 transistor OTA, but we are not using the tail current intentionally because the purpose. So it will be a chicken and egg problem if we use if you use a current source in your beta multiplier, then for that you need a reference that will generate that current source. So the tail current has been removed, and this is your differential pair, and this is and the size of this will be exactly similar to the unit elements. All this PMOS are same size, and this NMOS are same except this last one. Now if you run it, so it's already run. Now it's like you are at 1 and you have same. Okay, so I have to tweak it to match it. So if you want a bias reference, you just need a slight tweak. That is mainly because of your because the square law it's not exactly square law. Uh, okay, so this is quickly you can use it. Just you need a startup circuit, which I have not covered today. We can cover later sometime that how you can characterize beta multiplier. But this is a quick working design you will have. So just I have changed few things, and you see the VGS values is something you started with. Your currents are similar, and what two nodes you will take out for your PMOS? These two nodes. Wherever you need a PMOS current source, just take this and just connect like this. This goes to supply and this is there. And wherever you need an NMOS, you start with this. Just make sure you don't pick this because this is uh, 4 times, and just connect it like this. So yeah, now this is goes to ground. So you have a current source design with beta multiplier. Is this clear till here? Any questions?
Yes,
Like
sir.
the way? Yeah, go ahead.
No, no, no. Clear.
Okay, okay,
Sir,
cool.
sir, I have a
Yes,
doubt.
yes,
So, can we realize resistance of 65K on chip?
yes. It's very doable. Mega ohms, when you go mega tens of mega, it takes a lot of area. Even that is possible.
Okay,
65
okay.
so there are some if I want to, I can show you quickly what technology offers. So this is TSMC 65. You have diode, MOSFET, resistors. You have lot of two-terminal resistors, three-terminal. These are metal resistor. You don't use this because it takes a lot of area. These two are you can use it. In any technology, you will have resistor capacitor. Okay, now
Okay.
this is how we generate a current. Now comes to the other part, how you generate a voltage on chip. So let's start with again continue our discussion. So voltages are generated using bandgap references. These are some of the topics covered very well in courses. Okay. Can anyone tell what is a bandgap reference? Like how we make it? Okay, so the idea is right now we saw like how to design a current source. So wherever you need a current source, that beta multiplier is used. But there are places where you need a constant voltage, like your LDO design in which you have a reference. In ADCs, you need a constant voltage. So how we can realize on chip and how we can design it quickly. So let's assume that if you have a current source And by the way, we will use the same unit element of the current source, which we have seen. We will plug it here in our band gap. If this is a in every technology, you have vertical PNPs. The way it is fabricated, that's why it is called somewhere it's called VPNP. So if you have a diode, sorry, if you have a transistor, and if you connect the emitter and your gate, yes, it acts like a diode, and this VBE. So this VB, if you have a constant current 1 micro, if you inject it into a diode, so you get VBE. So your IC is equal to IS 1 minus e to the power minus VBE by VT. So, so this is some relation we have for the relation between our current and VBE. So if we want to write VBE, so let's call it VBE, that will be VT ln, and this will be whatever I naught we have divided by IS. Okay. If you so this is VT. So if what we can do is we can do a temperature switch. I can show you first like how we. So let's start with this example. Like I have taken this from the technology, and so this is VBE. I have injected 1 microcurrent, and in one case I just scale it by n times. So 15 mostly people do because of the layout point of view. So 15 plus 1 is 16. We can make a squarish layout. So if you have uh, two BJTs configured in diode connection, and one is in one you increase the area and just inject the same current. So if you plot VB1, VB2 and the difference, so I have VB1 and delta VB. So what I'm doing now is, sorry, I so, so we want a constant voltage across temperature. So here we will do a sweep. Suppose minus 40 to 125 degree, and then go to then simulate and see how VB1 VB. For more details, you can refer any book, analog IC design book, or any any video lecture. So the main thing is how we are extracting some of the current. So VB1 is you inject a current, but your area is minimum. Here you have increased your area. So this is how with temperature your VB is changing. So in band gap, what we do is, so this is called CTAT. CTAT means complementary to temperature. So as you increase the temperature, your value is going down. And this is VBE, delta VBE. What I have made delta VB is just took this difference. So same current injected, one is um, area is n times more than that. So if I want to write here, so what I have done is we have two V. So VB1 is VT ln n I naught by S. Let me call it 2, which one is larger. So I have two current sources, the same block. So this is n times, right? And this is VB2 and this is VB1. So what will be VB1? VT ln I naught by IS And when we take delta VBE, this VBE2 minus VBE1. So if you simplify, it will be VT ln N, because this I naught get cancelled. So it's a very linear relation. So this is one of the, in on chip, if you want a linear temperature sensor, just take this. And N is your ratio. If we keep similar N ln N1, you will never get VB. So that's why we keep a ratio. If this area is A, we keep it NA. You can refer Razavi's papers for this, or any book. So this is at room temperature is around 26 millivolt, and N we have to ln 15. So this VB. But the most important thing to see is what is delta VBE by delta T, and what is delta VBE by delta T. So these two numbers are required for design. So even if you don't get how these equations have come up, just if you take these two numbers from simulation, you can easily design a band gap reference, which we'll see now. So what Bandgap does is, so we have VREF, we try to add two parameters which are complementary with temperature. So if we see VBE1 plus if we have delta VBE, so one decreases with temperature, one increases with temperature. But we have seen in the graph, the slope is not same. So what we need is, we need a scaling factor. Can we have some scaling factor alpha here? So if we have a scaling factor, if one increases with temperature, one decreases with temperature, and it would cancel out itself, and you get a fixed value across temperature. So with this idea, people have started and came up with this circuit. Um, Before going into details, I will just quickly try to say how it works. So before that, if suppose this is VBE1 and this is VBE2, and if you apply a resistor between these two voltages, what will be the current value? It will be VBE2 minus VBE1 by R. So you can have a difference just if you can, if in any way, if you can do something like this. So your current is now, this is your PTAT current. The current is, because delta VB, so this is delta VBE by R. And this delta VBE is proportional to temperature, that VT ln N. So how this circuit was evolved was like, sorry, so you started with this design. And then this is your two. One way was to put a resistor through this, but then you will disturb the bias. So what people have done is, I know that this is VBE1 and this is VBE2. Put a resistor here with op-amp. So now, due to virtual short, so this is VBE1 and this is actually VBE2, and the current flowing through this is now delta VB by R, which is the PTAT current. So now this OTA will try to bias this current source, and with this current, we just mirror one and put it in another PTAT. Sorry, in another this VB. So this current which is flowing is delta VBE by R, and this is RL, and this is again VBE1. So the output you see from here is VREF is equal to VBE1 plus how much? RL into delta VBE by R. Is this clear till now? If you just go through a bit, read some lectures, you will come up. We will just see how in simulation we can make it. So now you see this ratio. RL by R, the ratio here is like R4 by R3. This decides how we can cancel it. So you have two, so your what will be your delta Vref by delta T will be your delta VBE by delta T and plus RL by R delta VBE by delta T. So if you know the temperature coefficient of VBE and delta VBE, just you need to select a ratio. And this is how, if you match this slope, you will get a not exact constant because there is no perfect there are some non-idealities, but this is the first iteration you can achieve. So let's go quickly. What I will do is I just selected one and this is my VB1. I will press M and D. So my slope is 2 millivolt per degree Celsius. That's clear. So I will write it down somewhere like my delta VB1 by delta T is minus 2 millivolt. Because it's going down, I have started with okay. And this is my VBE. So I will press N and D. This is how much? 227 microvolt. So I can say that it's 0.2 0.28. Right. No, 23. Okay, 0.23 millivolt. This is plus as we increase. So just these two numbers. So if I take that ratio, how much it will be 2 divided by 0.23. So it will be around 8.69. So what we have seen here is if we keep this RL by R as ratio. So what I do is I will keep this R as a variable and here I will set the ratio as if you do that calculation it's 8.69 times 8.7. So just by making this ratio and how we set the R is something I will just tell, but before that this is just the ratio. So in this I have kept it 75K. Suppose initially when I design I don't know this value. So how we set the ratio? So just let me show you the waveform, like how its value you can get. So in this, how it was made, the same uh, unit element called NMOS we have kept, and yeah, so this is your reference. Move to the, so you see this bell shape 1.2 volt, you can achieve. And then there are some more, if you want more accuracy, then you do some curvature compensation, so it become S shape. Yeah, so in this whole design process, what are the variables? I took this from the technology file. So there are only three sizes possible. To save area, kept the lowest one. This is 15, and this is the same replica which is needed. So just arrange this and a resistor, so this current. So quickly you can have one your band gap ready with this. You need to make an OTA for this, which you can try a different. So the PSRR, if you study a bit more, the PSRR of this band gap depends on the gain of this OTA. You need to make sure you achieve that gain. Yeah, so the missing part was um, in all this, yeah, so this is your how you set the current. Your current is delta VBE by R. So this is that R. And you know that this is the VT ln N. So if this current flows through this transistor, and if we want this transistor to operate at 1 microvolt, biasing is required, then you know this, you know this, you know this, you can set this R. So this is how that R was selected. So if you see here, a sweep was required. It was not that I got it for the first time. So what I mean is, I know approx it was around 80. So I can go from there, say, okay, 70K to 85. And I can run. So I made it auto, so it gave less number of points. But if you want a very fine sweep, you can also do that. In this way, I just see my VREF plot, and I know that I can set it. And the value of 75. Okay. While it is simulating, is there any question? Yeah, so this is how you see this. Yeah. So
Sorry, Miraj, I have a
yes.
question. When you are canceling the slopes, at what temperature
Yes.
you was doing so?
Okay, so it's a slope with so this is with respect to temperature. So I'm calculating slope with respect to temperature. It's not a fixed temperature. So it's suppose this is 0 degree and this is 80 degree. So I need this slope
No,
and this slope. So I'm
but I
sweeping
mean,
my
it will perfectly cancel at a certain temperature, right? Not across temperature due to non-idealities.
yeah, non-ideality. So this is how we let me show you that. So I know that this slope and this slope I'm trying to cancel here, but due to non-ideality, you see the bell shape. This bell shape, uh, this bell shape. So this is a flat part. Here you get almost zero temperature coefficient. So uh, you need to like consider a bit more design and mismatch non-ideality. So the reason I started with this is one of the simplest band gap. But in reality, you see this, you want VB from here and Q3 and Q1 are same. So in all current designs, we don't use this architecture. So this was the very beginning, earlier days, people used this way. Now we put a resistor here. Now the non-idealities mismatch between Q1, Q3 comes down to R2 and R3. So if I can quickly show, so so how much current here it is going? Delta VB by R, and this is virtual short. So this current is VB by R, or the VB1. So now in this case, your current is VB by R1 plus VB1 by R3. So this is how your current goes, and this is your PTAT, and this is your CTAT. The good thing, the drawback of this was your output was VB1 plus your R4 by R3 into delta VB. So you can only set either the voltage or compensate for your temperature coefficient. But here you get both knobs. So R3, R1 helps you to compensate the temperature, and RL and R3 will help you to achieve whatever voltage you want. So this segregates. So this architecture is better. But for initial simulation, I started with the other one. So I have not covered non-idealities and all, but the purpose was how quickly you can design a block, and then when you run it, you find out, okay, this is my non-idealities. Then I need to know a bit more that what is causing and trying to solve that. I think mm, I didn't answer your question completely, but we can have a separate only on Bandgap. We can discuss separately sometime later. Like the offset of this amplifier, your OTA will affect the output and how you try to mitigate. What are the numbers you play with? But today the purpose is to like how quickly we can have a working design, which is 80-90% close to what we want. And then we just go corner, Monte Carlo. There are many things we have to do. So anything else or any comment or feedback or something if it was not very clear? So I think this band gap was a bit, I covered it in it quickly. If you can go back, if someone is not clear about it, you can go through some lectures. But simulation wise, it will be very straightforward. So everything started from a unit element. With this, we are moving towards it. And we quick, so there are, you just by seeing equations, what ratio we want, you play with it. So you can design quickly in maybe 15 minutes, 30 minutes. You will be very close to what you want. Anything else? Or it was a
No,
bit
no.
heavy, not much clear.
Thank you, Miraj.
Moin, is that clear?
हाँ सर लाइक बैम्बा सर्किट के बारे में तो पढ़ा हुआ है तो इतना इश्यूज
Okay,
नहीं है उसमें
okay, okay.
non-idealities actually if we can take up some way specifically after layout how much the design changes and how do you compensate for layout variations जैसे कि प्रज्वल ने भी पूछा रजिस्टर का रियलाइजेशन कर लिया you
Right,
said that रजिस्टर का रियलाइजेशन कर दिया but
right.
compensating that changes due to layout that also
Uh,
I have a bit
okay, okay.
gray
So
area
it's
in that.
okay, okay. So it's not always about the layout. Even process variations are there,
Hmm.
non-idealities are there, mismatch are there.
Hmm.
So yeah, so in that case, I can think of something to take. Okay, so we can have one more for mitigating the, in actual chips, so this resistance plays a big role. So
Hmm.
there is a series of resistors put on it, and just you, it's like tuning this resistor after fabrication.
Hmm.
So what I
Spec-
mean is, um, something, I know that my resistor will vary across corner. Even resistor has its own corner. So you have multiple switches like this.
so, trimming a concept you're asking.
Yeah. It's a trimming
That
approach.
is also required, yes.
Yes. So this you can do post fabrication when your chip has arrived and you
Hmm.
want to meet this spec. And there are some concepts
But
like chopping, auto zeroing for suppose if this output offset is there, how you
sir, but
can,
that implementation is area hungry, right? If you add trimming to your chip.
yes, so it's a trade-off. So
Hmm.
sometimes you have trimming some circuit technique, like for this band gap reference, if we have a if there is some offset in this, it will reflect in the output. So you will have your offset at an alpha offset term as well. So from design point of view, if you don't want to use chopping, then you need these terms to be much greater than offset.
Hmm.
So then, so sometimes approximation helps, in which your one parameters is much smaller than the other. So it
Hmm.
affects it won't affect much. So then there is like you see like okay, I have to increase this size. So there will be trade-offs, but one, and if you want low area and then if you want this offset effect not be there, then you use chopping here. By
Hmm.
this way you can mitigate offset. So
Oh,
based on what non-idealities you are targeting, you can do it. So so the temperature coefficient of this, which I showed in simulation, is it may be good enough for some application. So this architecture works very well for some application, but if so, it de purely depends on your application. Like For example, if you have suppose multiple block in your signal chain, so if you want to optimize the noise, the lowest noise decides your whole SNR of your chain. So in that you need to see like what is, so if you start with a spec, then we can if you give me a spec, then we can have one design example where from spec how we try to achieve from the simplest design and how we will go and try to meet that. And it is very specific to design, like this band gap, if it is used in an LDO, you don't need chopping. But if there is an application in which LDO noise should be very low, then this needs the flicker noise of all this and noise of these transitions to be taken care. So I would say that uh, from spec to implementation would be a good way forward. So is there any spec which you are targeting? Then we can have fully focused on that block design. Is there something you want, or some other block other than band gap kinds of?
Sir, can I I have some ideas at mind, I want to explore. Can I message you later about? We can have discussion on those topics then.
Okay, that's fine.
And
Any
some MTechs are there
Yeah.
of so I'll also discuss with them if they have any learning process wise, if they want to hear an
Yeah,
IT moment, then
yeah,
I
sure.
can come up with something. Because this is
Okay.
helpful because practical design point of view, theory they can learn from analog courses here and
Yes.
from IT matters, but design perspective, this will be helpful. Quick design and how to improve it.
Yes, yes, sure. We can. Yeah, anyone else want to say
Sir,
something?
I had a request.
Yes.
Sir, can you give an introduction about how to use Monte Carlo for mismatch calculation and how it works?
Okay, so Moin, can you write it down? Just send it to me later. So that's fine. I
Okay.
think what we covered here. Yeah, so yeah, you can observe all this in your simulation, and you can exactly see that okay, my V2 mismatch, how it's affecting the current mismatch. Okay, that's fine. That can be a good topic.
Okay, sir. I'll write it down and float out something for you so that we can have a discussion on those topics as well.
Okay, okay,
Thank you, sir.
okay, we'll end now. Thank you. Yeah.
Thank you, sir. Thank you.